Hi guys, today I wanted to share yet another problem with you. This one is red, so like 2600 rated, but it is not that complicated as our first red problem, which we had on Tuesday. This one is a little bit easier. So, and this comes from a recent Div 2 round. I actually kind of had several ideas about it during the contest, but couldn't complete implementing them. So I wanted to upsolve it, so that's why we have this problem today. And also because it's red, and I promised a red problem for you yesterday, so yeah. In this problem, if I may remind you the statement, in case you don't remember it. So we have or in case you did not participate in that specific Div 2 contest. So we're given a tree with n nodes. We construct a sequence of integers doing the following operation exactly n times. We select an unerased node u. We assign a u, the number of unerased nodes adjacent to u. Then we erase the node u along with all edges that have it as an endpoint. And then we want to find the number of sequences such that number of possible sequences to obtain such that the GCD of all the numbers is equal to k. So for example, in this case, we may delete vertices in, let's say, order 2, 3, 1. Yes. So then when we delete 2, it will get 1. When we delete 3, it will get another 1. And when we delete 1, it will get 0 because all its neighbors are already deleted. Now, you see, my problem during the contest was that I could not read. Because it actually explains that if we delete 2, 3, 1, and the answer will be 0, 1, 1, because when you delete a node, you assign to the corresponding element and not just construct the sequence one by one. So that subtle thing that I missed during the contest meant the problem becomes completely unsolvable. I believe it becomes NP complete. So the point is in this case, 2, 3, 1 and 3, 2, 1, they kind of yield the same sequence, but some other updates may yield another sequence. So it was not clear to me how do we distinguish. It turns out that we always put the number of adjacent nodes to u at the u's position of the array. So yeah, but unfortunately I can't read, so couldn't solve it during the contest because after. Okay. So what I figured out during the contest was that the answers are mostly zeros, because AU, they count edges in a way. So when we delete 2, you may have noticed that I highlighted this edge because this is what yields a 1 here. It's one edge that goes out of 2 that has not been deleted yet. So because AU count edges that go from the outgoing edges from u at the moment of deletion of u, it follows that sum of over u from 1 to n of AU is equal to number of edges, which is of course for a tree equal to n minus 1, and therefore it's impossible that all numbers are divisible by k if k does not divide n minus 1. So if this happens, then the answer is 0, and therefore we only want to consider such values of k that divide n minus 1, which is like, I believe, usually we can have a naive estimate of like square root of n, but on average it's much better. So yeah, so what happens is that we want to solve the problem, in fact, for like fixed k. We don't need anything else. We just want to, like, given a fixed k, determine whether it's possible to have GCD equal to k. And you may have noticed that I just said it's impossible for all integers to be divisible by k instead of saying that it's impossible for GCD to be k. Because the difference between being divisible by k and having a GCD of k is not that big. To be precise, we have to check that GCD can't be a multiplier of k. So like, if for all I from 1 to n, ai is divisible by k, right? And there does not exist some multiplier j such that this same condition holds for jk, then it follows that GCD is equal to k, right? Because like GCD is equal to k when all numbers are divisible by k and there is no bigger number that divides all of them. And naturally that bigger number, we can, like, it's not difficult to prove that this bigger number, if it exists, it must be a multiplier of k, because k already divides all numbers, so GCD should be divisible by k. Otherwise, it's not the greatest common divisor. So yeah, like now you may know some facts about how many numbers of such form there are. Hopefully, if you ever implemented sieve yourself and thought about it for like several minutes, and you should be able to realize that looping over all k's and then looping over all j, such that kj is at most n, and is of n log n overall. Because for k equal 1, there are n such values of j. For k equal 2, there are n over half such values of j, n over 3, etc. Go all the way up to n over n. And then you recognize that this is more or less the integral from 1 to, let's say, n of n over x dx, which is like n is a we can't think of n as a constant for the moment. So n goes out of the integral, this integrates to log, and log of 1 is 0, so what you get is n log n plus some constants. Now that constant can be determined more precisely. I believe it's called Euler-Macron's constant or something like this, Macroni, not exactly certain. But yeah, so this thing is fast, and therefore what we really want to do is we want to check whether it's possible for some specific values of k that divide n minus 1. We want to check whether it's possible to perform deletions in such an order that all ai's will be divisible by k, and from that array we'll be able to restore the answer using values of the form jk. And you may have noticed that I said we want to check whether it's possible to restore, And you will very soon see why I say if it's possible, instead of saying how many ways. Well, the thing is, we already said that a U counts edges, and each edge can be counted towards either of its endpoints, but not towards two, and certainly counted towards one of them. Therefore, while trying to construct an algorithm that actually checks if it's possible, or like counts number of edges, it's usually DFS, right? You already have like square root of n overhead, so it's unlikely that you can afford n log n for each check. So you must have something linear for a graph and let's say dynamic programming. It's most usual DFS. So what you do is, let's say k is equal to 2 for this graph. We know that there is a way to do it, but let's see how it proceeds. So like DFS goes here, then it goes here. Looks at this edge, at this vertex, it says, okay, like I have exactly one edge to parent, I have no edges to children. So like a number of edges that I get should be divisible by 2. So I now have 0, it's divisible by 2. If I add 1, it won't be divisible by 2 anymore. And in general, if there was like 2 edges, then adding 1 it also makes it not divisible by 2. So it's kinda like obvious that this edge should get to 1, and DFS exit this vertex goes further, and for each edge, like you can see that if this number is already divisible by k, then it's kind of obvious that the edge goes to the parent, and then it gets counted in the parents. If, however, this number is not divisible by k, let's say there is exactly one edge, it goes here, and it was counted towards the parent, then you say like, okay, I have one edge here, right? And I need to be divisible by 2. So I'm currently not divisible. The only way I can get more edges, because all my children, in case it was not clear, because I haven't said it, DFS in this case works in post order. So we first process all children, and then we process the current vertex. So I can't get to any more edges from my children, and I'm not divisible by k at the moment. So I have to borrow, or rather like take once and for all the edge that goes from my parent to me. And luckily in this case, like I got this edge, I had 1, I got 2, 2 is divisible by 2. So now like this is a correct assignment for this vertex. If, however, let's say in this situation I have one edge going from my children, or from my child, and k is equal to 3, I try to borrow this edge, it gives me a value of 2, and it's still not enough, then we can immediately exit. Because once again, like this assignment is one of a kind. You can't, like it's uniquely determined by our algorithm that builds the assignment. So if we ever see that like neither this nor this gives a valid assignment for any vertex, we can immediately exit. And it becomes impossible to get any assignment with k equal with given value of k. If it's possible, then assignment is uniquely determined. So we already know some values f, summary f. Now that most of its values are zeros because n-1 is not divisible by the corresponding case. Some of its values are 1s. Some of values with k dividing n-1 are still there. And well, you may have noticed that what I everything I said applies only to k which is at least 2, because for k equal to 1, every assignment is divisible by 1. So overall, there are 2 to the power of n minus 1 assignments, because each edge goes either to one of its endpoints. There are n minus 1 edges, so product rule. And therefore, we get 2 to the power of n minus 1 here. Now you may say, like, wait a second, like the sum of this array is not what we want, clearly. So this is of course because we still haven't processed this part of the solution. And then our actual answer, say array h, will go as follows. So like, we look at each position, we originally take value of f at this position. When we look over all multipliers and we subtract them, so sort of inclusion-exclusion formula. For example, here, I believe that this corresponds to a value of 4, this corresponds to value of 8. So this is in fact divisible by this. What actually happened here is that we have, like, let's say, one assignment in which all values are divisible by 4, and one assignment in which all values are divisible by 8. It's clearly the same assignment, right? Like, because this assignment has to be counted here. And if it's 1, 1, then it's the same. So this value is actually 0. 0, 0 remains 0, and then here we get, like, we subtract this assignment. You get to the power of n minus 1, and then minus 1. And overall, this sum is correct, so it looks like it should be the case. So, our solution consists of several parts. I guess I can write them down. Let's try it. So first is read the statement carefully, I guess. Second one is, I believe it's like sometimes most of the answers are small, let's say 0, 1. Next idea, it's hard to formulate it like in normal words, but I will say that 2 sieve loops are of n log n overall and can be used elsewhere, because that is clearly important. Then yet another idea is perhaps checking some conditions on a tree often can be done with DFS. Because that's common. And one last idea is, I would say, like, look for applications of inclusion-exclusion formula. Because what we used with like 2 sieve loop, that's actually inclusion-exclusion, right? We either counted some values, like we said, okay, there is an assignment where all values are divisible by 4, but in this case, GCD is actually greater than 4, so we have to subtract back. So like inclusion-exclusion, it is in its simplest form. Or not even inclusion-exclusion, I just call everything where we overcount and then take back. I call everything of this form inclusion exclusion. Formally speaking, inclusion exclusion is like just one formula. It is applied in a little bit different situation, but hopefully that does not confuse you. So I think that it's time to look at our implementation. Because everything is computed modular, we actually needed to compute. Oh, very interesting. This solution is actually incorrect. No, that is correct. Okay, but it's very subtle. Okay, so we have like everything is computed modular. I mentioned that f at 0 is equal to 2 to the n minus 1. So this has to be computed modular. I have this function here for this. I guess it's not necessary because like it only gets computed once. So you can as well compute it in of n time, but whatever. If you have this function, then why not just copy paste it? I don't know. But I actually typed it myself. Now that I'm thinking about it, maybe it was possible. Maybe it was better to just have like power of 2 computed naively, but whatever. I mean, it would be less code, right? But regardless, we read our graph. We will have some DFS. DFS gets called here when we fill the value, I guess. By the way, I think this should be like this. This really should be like this. Okay, well, yeah, something like this. It's like in this DFS gets called here when we compute values of f. So once again, we have like our modular power. We'll power all values of k. We only do something when k is a divisor of n minus 1. We process our DFS. DFS returns values as follows. If it returns -1, then it's impossible. If it returns 0, then it means that the edge went to a child. If it returns 1, it means that edge went to a parent. So if it is -1, then we don't have an assignment. Otherwise, we have a unique assignment. Then we have the sieve loops. So we loop our all values of k. We only check for values of k that are divisible by the divide n minus 1. We say like, okay, originally h of k is f of k, then we loop our all multipliers and we subtract the corresponding value. And then just print. So now the important thing that remains to be discussed is DFS. So obviously you need some markers of whether the vertex is used or not. And you count edges that you get from children. So you loop our children and check if it's impossible for some child, if it's impossible to assign edges to this child, then we return -1 from ourselves as well. We can do it straight away. Otherwise, if the edge goes to parent, then we increment the count of edges that we got from our children. And we check if we are already divisible by k, then we return 1, because like it means that we don't need, and in fact it would hurt us to take an edge from our parent, so our edge goes to our parent. Otherwise we take an edge from our parent. If then our assignment is valid, then we return 0, meaning that we took the edge from parent because we absolutely needed it. Otherwise we return -1 because like we had only 2 options: to skip the edge, to take the edge. Otherwise we failed because we could not do anything. So that's it. It is quite slow, but keep in mind that time limit for the actual problem is 5 seconds. So like it's increased like a lot. All right. and therefore it's not that bad that our solution works in 1.5 seconds. I guess it's kind of happens quite often for difficult problems that have several parts to them. So that's more or less what I wanted to describe today, I guess. I hope you found some of these ideas educational, useful. You may see problems that don't require all of these ideas combined, but let's say like one or two of them. It's already quite common to see these things about like sieve, right? That two sieve loops running off and again overall. It's quite common that sometimes the answer exists only for divisors of some number. So again, we leverage the fact that each number has not so many divisors compared to itself. So like, I would say that number of divisors of n is generally much closer to log of n than to square root of n. So you may sometimes see like the complexity of the form of n times number of divisors times log, because like, well, it's generally considered that of n squared of n log n is not great, because usually also have some not that great constant with it. So yeah, it may sometimes be slower than even of n squared, as I guess Radevish would tell you. But yeah, if square root is actually number of divisors, then it's more or less okay. So yeah, that's it for me for today. I hope you enjoyed. I hope you learned something new. And I'll see you tomorrow. Tomorrow is actually a weekend, so it may be the case that I will have some time for like a full length contest, but we'll see. In case I don't, then I will just release a one problem video in the morning. In case I do have time for a contest, then we'll have a contest in maybe a video in the morning, but not so sure. It's most likely it will going to be one of the two. Let's hope for a contest, but we'll see. So with that, I wish you a great day, and I'll see you tomorrow. Bye bye.